UH Manoa in NRM. So hopefully his talk will spark various interesting collaborations today and get our minds thinking more on how we can integrate with what he's presenting. Just a brief background, he graduated with a bachelor's degree in geography in 2004 and a master's degree in 2006 from Ben Gurion University in Israel. Then in 2010, he earned his PhD at the University of Newcastle in Australia, working on soil landscape evolution modeling. Then between 2010 and 2012, he held a postdoctoral position at the University of Colorado in Boulder, working on global scale sediment flux modeling. And then he joined the University of Alabama in 2012 and established a surface dynamic modeling lab, SDML, in 2013. So in recent years, his research efforts at his lab have been focused on numerical modeling and analysis of riverine fluxes and remote sensing and analysis of flooding. And today he will talk and share a little bit of his work on that, with the title of the talk being Riverine Research Across Scales, from Global Scale Sediment Modeling to Event-Scaled Flood Analysis. So please join me in welcoming Dr. Sagy.
Anything else on bias?
It's okay.
We shared our mispronunciation of our first name. I'm used to it. Well, thank you very much for being here. It's a great honor. I've been, as Neil said, I've been here since August, working in fact, same lab. I mispronounce her name all the time as well, in Enron. And actually, Neil's segue was gave me a really good segue because I do want to give an overview today. Not focusing on one project particularly, just give an overview for the purpose that he actually mentioned. I don't think I said that in my email. Really sparking some potential collaboration. So if there's something there that I kind of skip over or talk very quickly about and you want to know more, I'm around. I'll give you my email at the end. I'm very happy to talk about it with anyone. I'll be here until August of next year, so I'll be around for a while. So I do want to touch, if time permitting, on two subjects or two main topics that I've been working on in my lab for the last couple of years, which is this global scale modeling of rivers and this more fine scale analysis of floods. So I really like, I hope it shows that, yeah, it looks pretty good. Like this figure that I kind of captured from Google Earth. Anyone can guess or know what are we looking at? What river basin are we looking at, basically? It's not north-oriented, by the way, so it's in the middle of North River there. So this is the Amazon, and it's my favorite basin for obvious reason, as someone who's doing a lot of global scale analysis. And you can see from space how much sediment it's carrying. So I'm going to talk a lot about sediment. And you can see up here the Andes mountain. Yeah, that's very sensitive. The Andes over here that supply most of the sediment to this massive river. And there's another interesting feature here. I'll actually just point to it. This little black line here can, again, being the professor that I am, anyone know or guess what this little black line is? This is the Rio Negro River in the Amazon. And it's a very interesting river because unlike the Amazon, it's there's very little sediment in it. It's draining the Amazon forest, provide very little sediment. There's relatively little topography in the Rio Negro Basin. And the confluence of the Amazon and the Rio Negro is actually a very, very interesting one. There's a city there called Manaus in Brazil at the confluence of these two rivers. And one of the main tourist attractions is actually going on a boat from Manaus and look at the confluence of the mixing, or actually the lack of mixing between those two rivers due to different temperature and density of the water. So that's just kind of a case study that I like to show and to kind of frame a little bit of the kind of work that we do. And by the way, the mixing of that, because these are very large rivers, the mixing can take over 100 kilometers until the two rivers are fully mixed, sometimes even longer depending on the season. I don't think I need to convince anyone around here why we need to worry about rivers or freshwater system, right? They're undergoing massive pressure from anthropogenic changes. On top of that, we have major climate change occurring in many basins around the world. So the combination of these two stressors or changes, depending on how you look on it, can introduce major issues or major concerns for freshwater systems around the world. And obviously, as a society, we rely on them very heavily. So what we argue, our perspective from it is we want to look at it from a global scale. Most people, for very good reasons, they look at specific basins or catchments, and they do a lot of good analysis on that specific study. We want to look at the global scale, and we argue that there's a lot of merit in doing that, at having a global perspective that builds on the small scale perspective. And what we've done in order to do this analysis of these studies is we developed a very unique model framework that can simulate both the water, but also the sediment, and to a lesser degree, I'm going to talk a little less about nutrient fluxes in global rivers. So it's a global scale distributed model, and I'll show you some case studies that we've done. I'm going to very quickly go over the model. I can talk hours, and I used to focus a lot of my presentation about the model, and someone told me that's a little boring. It's not boring to me, but if you're not really into the modeling, I guess it is kind of boring to hear a lot about the model. But in a nutshell, we call it WBMsed, and it's a gridded model, so you have grid cells, pixels, fully distributed in both space and time. This was the first paper we published about it, and it's an open source, so anyone can use it, although I must admit that the learning curve of actually using it is quite steep. We need a lot of data as well, but I have in the past, me and others that have been working on it, help others to set it up and use it. It actually builds on an existing, quite a model that's been around or been in development for many years, a hydrological model. So we took a hydrological model, a hydrological modeling framework, global scale, there's a few of those around, and added sediment to it. That's basically what we did. Now the hydrological model is called WBM+, and it's your kind of somewhat standard hydrological models. It's global scale or continental scale. It calculates the water balance at the grid scale and transport the excess water downstream into the river channel. And so you have, evaporation, precipitation, groundwater intake, and so on, all the usual suspects that you get in hydrological modeling. One of the unique features of WBM, I would argue, even though it's probably not, I know for sure it's not the most popular model out there for global scale hydrology, but it is, I think, one of the strongest because it has the most explicit anthropogenic parameterization in it compared to others, including water uptake from groundwater, water uptake from reservoir, dam operation for controlling flows, and so on. One of my contributions to the hydrology side of that model was this kind of schematics down here. We introduced what I call a virtual floodplain. And again, this is one of those examples. I could talk an hour about that alone, which I'm not. But basically, models like this, global scale models, continental scale models, and often even small scale models, have an issue with overbank flow. Basically, they don't count. So it means that the rivers have an infinite capacity to transport water. Now, in small scale, it may not be a big deal, but if you're trying to do global scale or large scale and temporally explicit modeling, it's a big deal because it means that there's never floods, and floods are major control and have major effect on the amount of water that reach the ocean, for example. Because a lot of it is stored or mitigated within flooding and within the floodplain. So I introduced this concept to the model framework. I'm actually pretty proud of it, to be honest. It's been a while, and I adopted an existing approach that someone else developed for global scale modeling, and it actually works quite nicely. So it's basically estimates what is the bankful discharge that you get at each location, and if the model exceeds that discharge for a given day, it will just remove that water into what as I said, virtual floodplain, and then the water will be introduced back into the river once the water recedes. So it's kind of produce a much nicer hydrograph, more realistic hydrograph. Now the sediment component, we started with a suspended sediment. Those of you who don't know much about sediment, in a nutshell, sediment can move in several forms, one of which is suspended, so particles that are small enough to be always in suspension within the water column, as opposed to bedrock, which I'm going to talk later, which is flowing very close to the bed of the river. So we introduced, this is a new model that this was the core of my postdoc work, was to develop this. We use an existing equation that Savitsky and Milliman introduced in 2007. They was trying to estimate the amount of sediment globally that goes out to the oceans. And as you can see, there's quite a few parameters there. Very quickly, we have lithology, we have area of the basin, we have how much discharge we get, ice cover, we have some anthropogenic factor I'm going to talk about later, reservoir capacity, how they affect the amount of sediment, and so on. There's a few more there that I don't want to go into that. So the whole scheme was not just to introduce this specific equation, but to make it spatially and temporally explicit. So you don't just estimate how much water you get at the outlet, but everywhere along within the basin itself. And I'll show you some maps in a minute. When we published this 2013, although originally it was 2011 online, one of those special issues that it took a while until everyone submitted. This was the first, and still I think only one of two global sediment models. There was another guy that developed another model. This is the only spatially and temporally explicit model that do global sediment. And as you'll see, there's quite a few people who use it for their own research. Some of them in direct collaboration, some of them just use it by themselves. Another very recent, not yet fully published module that we introduced to the model is bedload. That use also some existing equation, and we had some issues with, we're still validating it, so that's why it's not really published yet. It looks pretty decent for a first crack at bedload at the global scale. One of the things that we did publish in Journal of Hydrology, this paper here, one of those surprises that I keep having in my career is that in order to do bedload, we need to know slope, because the energy of the water is a major impact of how much sediment is transported in saltation down on the bed. So you need to know the slope of the river, basically, at any location. And to my surprise, or my naivete, no one have ever developed a global river slope layer. There's some challenges, again, and this is one of those examples. I'm not going to go into that right now, but there's a lot of reasons why it's actually kind of difficult to do, because large rivers have very, very small slopes, 0.00001% or something like that. So actually capturing the slope is very difficult from standard slope calculation techniques. So we developed this global slope layer, and that's the part of this project that we actually published so far. And we recently changed that or improved it. That's why I didn't publish the bedrock yet, because I need to rerun it basically. I also mentioned nutrients. I know probably a lot of people do ecology mainly interested in nutrients, not so much sediment per se, or as a mineral, but more as the nutrient that it can carry. So the nutrient component of this model, at this point, at least my nutrient component to it, was based on particulate nutrients. So the kind of nutrients that piggyback on the sediment when it's coming downstream. So we developed, again, use some existing equation that people have developed for very lumped estimation of particulate nutrients. And we did it within this model to generate a spatially and temporally explicit. And again, this is the only kind of its, the only model of its kind for doing this at that kind of resolution and both space and time. Now, to give you a sense of, this is the last slide of the actual model itself. So the model framework run at daily time steps. We don't necessarily look at daily output, but that's the inherent time step that it used to calculate the hydrology and therefore sediment. We run it at decades time scale. So this is, some people do like geological time scale. That's not the kind of model that you use. And you can do as many decades, I guess, as you want, as long as you have time and the input to run it, right? You need precipitation, particularly, and temperature, which is big challenges for doing hydrology at very long time scales. We run it at this point at 6 arc-minute resolution, so it gives you a grid cells of 11 by 11 kilometers, just to give you a sense. I know a lot of you are probably working on Hawaii, obviously, and Hawaii rivers, which are, see this little white dot here? That's it. So there's very few pixels that the model at this scale represent of Hawaii, right? 11 kilometers, that's pretty wide. But I'll show you in actually the next slide. I'm going to show you some development on that. And it takes at that resolution about 1 hour to simulate 1 year of simulation. So it's pretty efficient in that regard. Now the model framework is flexible enough that you can run it at much higher resolution, more locally, if you have the data. And this is just an example using 15 arc-second for the Northeast US. And this is something very, very new. I just took this screenshot today. And last week, I just started working on it. We're trying to see if we can run this model for Hawaii, in this case, Oahu. Obviously, we're going to start small. And this model actually is not really built for this kind of scales. But I'm going to see what happens, basically. Because I'm so familiar with this, and I said, why not, right? Why not try to run it? I need to change some of the source code to actually deal with this kind of resolution. I started with 10-meter DEM that I got. I think it's too much. I'm trying now 30-meter and see how it looks. So this is just a screenshot of looking at the sort of the basins and later the network that it's going to do. All right, so that was it about the model. Let me talk very quickly about some case studies application that I've been using. And once more, if you were interested in any of these and you want to talk about it at any point, just let me know. And this is some eye candy that I'd like to show. You remember we talked about it at the start about the Rio Negro. This is, again, one of those Google Earth things zooming in on that confluence. This is Manaus that I was talking about, this city in Brazil. This is the mixing between the two rivers. This is the Rio Negro come in. You see very black, right? Very little sediment. And then the Amazon, or Rio Amazonas, I guess that's the more official name. And this is the boundary between the two. And as I said, it can take over 100 kilometers for the two to mix. And the reason why I like to show it, this is model results from this. And we actually do a pretty decent job here with the model, which was kind of nice. That's why I like to show it. It's kind of, as I said, an eye candy that I like to show. We are looking. There's a project on the horizon to actually focus on these very large confluences. There's very interesting things going there, both from a geomorphological perspective and also from an ecological perspective. The mixing of water with different temperature, different density, different sediment content, and therefore different nutrient content can have a very significant dynamics going on there that you want to look at it sometime in the future. The first case study that I want to talk about is the anthropogenic impacts. I think this is kind of fascinating when you start thinking about it at a global scale. We all know, as I said in my introduction, that anthropogenic impacts are very significant, right? We all know that. We see it all over us. But when you look at the global perspective, take the large-scale picture of that, humans are doing two conflicting impacts on sediment flux in global rivers. On one hand, we all know that humans or anthropogenic activity increase sediment by by changing the land cover, basically by deforestation and so on. We see it in Hawaii. That's right. You look at those after a big rainy event, you see all this sediment, and it's basically, or according to studies, much more than the natural signature of it. So this is not surprising. So as humans, we've been very, I call it busy ants, right? Digging up the soil, making it more erodible, and therefore increasing the amount of sediment into the rivers and therefore into the ocean. The flip side of that is ours being very, I call it busy beaver. We have been very active and very busy at damming rivers all over the world, especially in the US and Europe because they've been doing it longer, I guess. But there's now trends or increase in the amount of, I show some other case studies about it, a big push towards damming in Southeast Asia. China went over that phase in the last several decades. India is now going through that phase. So there's a lot of damming going on. And obviously, I said the US and Europe have been doing it for many years now. So what is the net effect, right? On one hand, we increase sediment. On the other hand, we trap it behind dams. And other estimates of Boris Marty in 2003 estimated that the net effect on the amount of sediment going to the oceans is a 30% reduction. That was their estimate back then. There's another estimate that also show a much more modest decrease in amount of water that goes into the oceans. So just fresh water, because when you put water behind dams, you allow more evaporation. You also take that water for irrigation and so on. But it's much less of that. So what we did was use the model and ran it into what we call two modes. One is pristine mode, which is remove all the human activity, remove dams, remove any kind of effect on hydrology, like irrigation and trapping, so evaporation in reservoir, and so on, and remove all the anthropogenic factors that affect sediment flux. We ran it without these humans, right? The pristine mode, we call it, and with disturbed mode. And all we did then, what's the difference? Very simple. Very simple GIS. The end result of it was a simple GIS. This was actually a master thesis by one of my students, which I'm still chasing to try to publish this. He got a job, as many of you know the story, and kind of lost interest, unfortunately, because I thought it was a really nice thesis. But anyway, once you start doing the analysis, and again, you can spend a lot of time trying to understand what's going on because it's very diverse. Some part of the river out of the world behave this way, other behave the other way. And this is just focusing on Southeast Asia because this is kind of the hot spot, as I said, for now, for dammings and also land use because there's a lot of economic development changes overall. I'll show you this table and the take home from it. So the top table shows the impact, potential, well, I should say potential, right? This is model result. So effect of land use, anthropogenic land use on the amount of sediment. And I kind of highlighted northern Asia. So 114% increase in sediment due to changes in land use. That's what the model predicts. And you know, you should take it with a grain of salt, obviously. It's very simplified. But the reason why, first of all, that's the highest number. But when you introduce reservoirs or dams into that mix, into this model results, the net effect in Asia is 0%, meaning, and we didn't mess with the numbers to get to 0. That's just how it ended up. So you introduce a lot more sediment, but you also put all these dams, so the net effect of the amount of sediment that goes to the ocean is 0 in more than time. Obviously, it changes over the years when you introduce more dams and change and the total effect that we got was very similar to what Boris Marty predicted, about 25 or 30%. I don't remember the exact number. Sorry. I thought I put it on silence. So, and then again, you can dive into these results, but just to I'm telling you this just to demonstrate the kind of work that we've done. This is a work, paper just published this year, another one coming. To look at river deltas. So this is colleagues at the University of Southampton in the UK, and they use the model, we use, I should say, the model to look at river deltas. River deltas are very interesting because they are extremely susceptible to changes in sediment. Because once you starve a delta of its sediment, it starts eroding. You add to it sea level rise, and anthropogenic effect like land subsidence due to groundwater and so on, you start getting into trouble because there's over 300 million people living in deltas, including several megacities. So there's a lot of emphasis, a lot of interest. I don't know if anyone here has worked on deltas, but at the global scale, there's a lot of interest in river deltas. And what Frances Dunn was doing, or she spearheaded this was a PhD work was to look at climate and social or socioeconomic scenarios. These are this table here. So we have those RCP, right, climate change scenarios, and then the SSPs, the social, I forgot what the acronym stands for, but social economic scenarios, how many people, what's the GDP, and so on. And she wanted to see, okay, given different scenarios, how much sediment is going to reach deltas in the future? What's the impact is going to be on humans and climate on deltas? This is a fresh, this is a figure that we just put. This is in a paper now under review, Nature Sustainability. Fingers crossed, it's going to be published. But she tried to summarize, okay, what are the main controls? So this is just one figure, right? So the heat map is the amount of existing reservoirs or dams, and those bulky square red is the future predicted dams, hydroelectric dams. So you can see the Southeast Asia, right? They have a lot of dams planned. Sorry, South America, Southeast Asia. And then we also have here around the Middle East and Southeastern Europe, a lot of dams are being planned. So Francis was trying to summarize, okay, what are the major impacts of the future? Is it going to be climate? Is it going to be dams? And so the colors here represent, so climate change driven is this yellowish, greenish color. Socioeconomic driven is this color, whatever you would call it. And then the red color is dam construction. Again, just showcasing this project, I thought it was really cool, and can tell you something about the risk or the drivers and the effect of the future changes on these very important locations, coastal locations. In addition to that, this is another project my own student, Ishana, is now working on. This is to do a very systematic analysis of climate change and how it impacts discharge, water discharge, and sediment. So she's going to use 5 different GCMs, global general circulation models, to look at climate change. We did each one 4 different scenario, RCP scenario, and she's going to do a whole suite of analysis of projected changes. And this is going to be the first of its kind to look at sediment. People have used similar approach to look at discharge and water discharge. This is going to be the first one that actually looked at sediment. And I'm kind of curious to see what she found out. This is just a very preliminary result she has. Another example of the use, this is a really, really cool project. I really liked working on it, and we're still working with. This is from a poster we presented at APU last year. Still haven't published or written a paper about it. But these two, Jules and Stephen Derby, was doing a lot of work on tropical cyclones. They did a lot of work on the tropics, especially Southeast Asia, the Mekong, and so on. And they observed the impact of tropical cyclones on sediment there. And they approached me. I went to visit them a few years ago, and they said, why don't we extrapolate that globally with your model? So the idea is very simple and although I think very interesting. They came up with a procedure to take the tropical cyclone globally tracks, right? You see all these colors here, and basically remove the precipitation for that day at that location of the tropical cyclone with a radius that I guess is corresponding to the strength of the hurricane. So basically, what they do by that is they generate a precipitation data set that is without cyclones. You remove the water or the precipitation that cyclone introduced. And when you do that, you can compare. So the right panel there on the top shows you precipitation amounts or percents or percent change in precipitation with and without tropical cyclones. So just isolating the contribution of tropical cyclones on precipitation. And it looks, what you would expect, right? The tropics and that are mostly impacted. And then finally, we take it and drive the model with those 2 precipitation data sets. So by doing that, you can isolate what is the contribution of tropical cyclones on water and sediment in rivers. That's the idea. And we get the result, the map, I know it's kind of hard to see at that resolution. The maps are reasonable, although we are, at this point, still need to convince ourselves that the numbers make sense. They are a little high in terms of the percent contribution of tropical cyclones. We need to convince, as I said. The problem we have is that tropical cyclones are obviously very energetic, but very short-lived, relatively speaking, events. The question is, can the precipitation data that we use actually capture these extreme events? That's why we need to convince ourselves before we go out and try to publish this. The map looks good. The numbers are maybe a little bit exaggerated. Quickly, another case study, very, very new. This is a paper that's hopefully going to be submitted very soon by Savitsky. Temperature. This may resonate with those of you who do ecology, for example. I don't know how many of you do that. But we actually approach temperature, water temperature, I mean, and from the geomorphological perspective, because changes in water temperature in rivers affect their density and therefore their sediment carrying capacity via settling velocity of sediment. And I have some numbers here that Savitsky came up with, calculated. They said that 25 C increase in water temperature can increase gain settling velocity by 42%, 85, 90% for the different particle size. So the bigger the particle size, the more, the smaller the particle size, the more impact it's going to have. And he calculated that for 62.5 micron particle size, you can have 90% increase in sediment transport. Basically, the argument we're trying to make in this paper is that temperature is important. Everyone ignores it. And they ignore it because they can't calculate it in a temporally and spatially explicit way. It's actually not straightforward to estimate water temperature in rivers, especially large rivers, because here's two examples that we use in this paper. This is the Mississippi River, and we just track water temperature and discharge down its main stem from the Rockies all the way to the Gulf Coast, and this is what these plots show. So the red plots show the water temperature, so it runs from about 10 degrees C to 22 on long-term average, so this is not for a specific day, and this is discharge, and you see those jump in discharge and less so jumps in temperature. This is when you have a major confluence coming to the Mississippi River, like the Ohio, and the Yellowstone also, I guess, is indicated here. So changes, and by the way, these are just 4 different days randomly selected that we looked at the temperature profile of the Mississippi main stem, and as you can see, they change quite a bit. So the take home is it can change a lot, and as a result, it can affect sediment a lot, but no one takes that into consideration because they don't know what the temperature is. An interesting thing of this, when you compare, so the Mississippi, right, it flows from, as most rivers, from high altitude to the coast, right, to zero. And then in the case of the Mississippi, it runs from high latitude to low latitude. So it gets warmer, air temperature gets warmer as it goes down its path. And if you look at the other, at the second example, which is the Lena River in Siberia, that flows from the south to the north. So it goes from higher temperature for low latitudes to high latitudes. So it's almost a mirror image of the Mississippi. One is getting from cold areas to warm area, and the other from the other way around. So that's why the temperature profile of the Lena is kind of going downward towards colder, and that can have a major impact as well, because as you go down, you have more sediment generally in the river. But now that the temperature profile is so different, that can have a major impact on how much sediment is actually moving. Now, the implication for it for ecology, as I mentioned, because as I said, like Ken mentioned, she worked a lot on that. The ecosystem is very responsive to temperature and affected by temperature and its change, and also affected by sediment and its change. So we still don't know exactly what it is, but that's something that we introduce new capabilities in modeling, and we can actually now do that. And by the way, the temperature model is really, it's been recently developed or updated, and it's a pretty good model from what the developer tells us. I didn't develop the water temperature. To extend that, in addition to temperature, another thing that affects the water density is the amount of sediment, the amount of mineral in the water itself. So this is another paper we hope to start working on when I get some time, is to look at the impact of both water temperature and sedimental density. And we started this project looking at those big river confluences that I mentioned earlier, because there it's the hotspot of change. Again, the Rio Negro, or some river that comes from the north, and a river that comes from the east, or whatever, they meet together. They can have very different amounts of sediment and temperature, and that mixing zone is potentially, well, it's not potential, people have looked at it quite intensively. It's very interesting from both geomorphological and ecological perspective. So this is where we are now going with this, looking more explicitly at water density. Yeah, okay, I think I'm good on time. So the next topic, this is the end of the global river modeling perspective. I want to very quickly talk about flooding. And this is a more recent, I guess, most recent theme that I've been working on, and I'll tell you a little bit why. It's also the most applied type of research that I do. And I really enjoy doing applied research. I've not done it much before. It's kind of rewarding, actually, to do both, both applied and theoretical research. Because when you do applied research, it can have immediate impact, on people, potentially, if they take note of it, right? But I'll show you an example. So the reason why I started working more intensely on flooding has to do with the University of Alabama. So when I moved there in 2012, 2013 or 14, I don't remember exactly, we were fortunate to have the National Water Center open on our campus. Probably never heard of, yet to heard of, maybe you have, I don't know. National Water Center was opened by NOAA, USGS, Army Corps of Engineers, FEMA, maybe there's someone else there that I'm missing. But it's a federal funded center. And the main player there is NOAA. They're the main leader of that consortium, I guess, of agencies. The point of the National Water Center was to centralize, as the name suggests, research, research development and operation at the federal level. So have less of a diversion or distribution as it does now, and have more of a centralized approach. They have an operational center there that just became operational. They're now manning it, and every time there's a big water-related event happening in the U.S., they are supposedly going to manage it from there. So that's going to be like the central location. So since they opened at the University of Alabama, and I can tell you offline why that happened in our university, why we got so lucky. I got involved with them, including they have, by the way, those of you may be interested every year, they have a summer institute for graduate students to go there. Those, if you have students that are interested in hydrology / especially flooding, but not necessarily just flooding, that's a good 7-week program, fully funded by NOAA. The only downside is spending 7 weeks in the summer in Alabama. The weather is not that great. But other than that, it's a great experience. And Eve Fan had a student there, she had a great experience there. Anyway, we started working on it the first year. I was a team leader in the last 4-1, or all 4-1, I guess we're on 10-4 so far. And we started working on the issues they have now. What they're trying to do, I didn't really tell them what they're trying to do. The last 4 years, their main goal in the National Water Center was to develop what they call a hyper-resolution flood prediction system. So we all get those annoying alerts on our phone, right? And more, I never got so many since moving to Hawaii. Right? Oahu is under flash flood warning. Should I do something? What should I do with this information? No one rarely does anything, right? I mean, what can you do with it? What they're trying to do is to make it less of Oahu or Kailua or whatever, or Honolulu, is more this street is expecting some flash flooding. Call the mayor or the police department, fire department, let them close this street for traffic. Let's evacuate these people. Right? It's not going to be that broad. And as you can imagine, that's quite a task. So as part of it, they developed something called the National Water Model, which we are hoping to improve upon for Hawaii. It's been implemented for Hawaii, but it's not very good. As I can tell you, that's because of the precipitation data that they have for this model, which is kind of very large-scale columns kind of precipitation data. But anyway, so they want to do this very ambitious thing, right? To tell you which street to close and which people to evacuate, so street-level predictions. But to my surprise, again, one of those surprising things that I got, there wasn't any real repository anywhere that you can take flood maps of floods that actually happened in the past to calibrate and validate your model. So how can you create models, forecasting models, without having the data to actually see if they make any sense or to calibrate them? So we got a little bit of money from NOAA through the Water Center, through Climatic, which is a UConn grant program, to develop what we call the US Flood Inundation Map Repository. It was a pretty simple idea, actually. Just let's look for floods that happened in the past over the US. We're not very picky. And let's see if we can map them using remote sensing analysis. That was the whole point of it. Sometimes people ask us for a specific flood, and we go and see if we can actually do that. Because the problem with remote sensing, you need to have the right image at the right time. If you're using optical remote sensing, you need to have cloud-free, almost cloud-free, which is always often a problem, as you can imagine, when it's flooding. And then one thing that I really wanted to do, so at the moment we have about 50 of these, probably now more than 50 of these images. One thing that was very important to me, I'm sure everyone here has experienced that, right? You want to get some data from somewhere. It can be a federal, state, whatever, private. They want you to create an account, right? They need to approve your account. Sometimes it's immediate, sometimes you need to wait. You don't use it for a year. Either they cancel your account or you forgot your password. And anyway, what I wanted to do is to make it completely open. No accounts, no nothing. And being in academia, I can do whatever I want, right? So that's the advantage. When I presented this and there was some USGS people there, they were not happy at all. They were actually kind of smiling about it. Because they have to abide by very strict bureaucracy and regulation. So just a quick screenshot. This is how it looks. This is the website of it. We have it's actually split in two. There's the map interface that we have, so you can zoom in and look at the flood maps that you want. There's also a table where you can immediately go and download them. You zoom in on something. This is, by the way, looking at on North and South Carolina. And the reason why I decided to take this screenshot, when the flooding was happening after Hurricane Florence in September, I got an email from Google, actually. Google is now starting to go into the flood prediction game, I guess. Maybe for their Google Maps or traffic, I don't know exactly why, or maybe just to be useful, I suppose, I don't know. But they sent an email and said, oh, we want to run a model, a hydraulic model for North Carolina. Do you have any maps? I told them, oh, well, we have those 3 maps. If you want, we can create some more. I don't know if they ended up using them or not and what they did, but just to give you a sense, if you click on a map, then as I said, completely open. There's some download links here. No one asks you who you are, where you come from. You download the shapefile, the polygon of the map. You even be nice to you and put a DN of that region and the link to the nearest USGS gauging site. So we call it the one-stop shop for modelers. So we try to really be useful. And it got some traction from the Water Center. People use it, some academic use it, and I don't know how many others use it because I don't track who uses it. Right? So that's that. We also want to go global. We only did it for the US because that's what we got funded for. We want to go global, but we have yet to get funded for that. So we have one flood outside the US at the moment, which is in Bangladesh. Someone asked us to create that. I guess we can add more. We had some more we did recently. The last thing I want to talk about real quickly relates to this and relate to my work with remote sensing of floods. So I have a friend, a colleague that runs the Dartmouth Flood Observatory, which is another one of those it's been a while, it's been in existence for a while, and they also map floods and provide flood mapping for emergency. And he told me that his clients, which is clients that don't pay, right? It's people like the World Bank, and who else? I don't know, a bunch of other relief organizations. They said they want to know not just where the water is, but how deep it is. Because how deep the water is actually very important for emergency response, right? You want to say, as the former chief of the fire department of Austin told us at the Summer Institute once, we want to know if people are walking, swimming, or swept away. He said it 3, 6, 9 feet. That's what he wants to know. And also for damage assessment, right? Because if a building, you see there was water around that building, but it's only a couple of inches, it's not bad. But if it's a few feet, a few meters, that's much more significant. Road closures. Anyway, there's a lot of reasons why you want to know how deep the water is, not just where it is. Now you can run a model, a hydraulic model, and simulate the fluid dynamics, but that requires quite a bit of input data and quite a bit of calibration, which really it's challenging. It's challenging to do, especially in emergency response mode. And if you look at very large scales as well. So I took the challenge of that, the head of the DFO, the Dartmouth Flood Observatory, and we developed what we call the floodwater depth estimation tool, which uses, instead of fluid dynamics, it's just used terrain. And this is another one of these surprises that no one had done it before this way. Other people have done different things. But the idea was, right, these days we're pretty lucky. We have DEMs everywhere, especially in the US. The resolution of these DEMs is getting better and better, higher and higher resolution. So we know what the topography looks like. We know where the water is from the remote sensing data, right? Someone has used satellite to map that. So let's figure out a way how to combine the two and come up with an estimate of water. In a nutshell, the approach is to take, if you look at it at a cross-section, it's pretty simple. If you know what is the maximum depth of the water, the flood water, like let's say 100 meters above sea level, then any location within the flooded domain, you can calculate its water depth just by subtracting it from its DEM value. Now the challenging bit was to make it in 2D, right? And to make it spatially explicit without relying on cross-section. This is I don't know if it's complicated, but this kind of schematics. It's basically a GIS approach, terrain analysis GIS approach. We published it recently, and we got actually better than expected results out of it. We compared it to a fully resolved hydraulic models, and we got actually, as I said, much better than expected results. Obviously, it's never perfect. Sometimes it misses quite a bit under certain circumstances. But when I started this, I said, okay, this is going to be nice, but I don't expect much, and it got much better than I expected, which is always a nice surprise. And we started using it. It got quite a bit of traction, actually. We started using it for the Global Flood Partnership. So I'm a member of the steering committee of the Global Flood Partnership. I'm sure a few of you heard of it, but it's a partnership of academic, practitioner, end users, government, whatever. Whoever wants to be a part of is welcome to share data and forecast once a flood or a flooding event is happening or about to happen. And this is mainly useful for developing countries that don't have capabilities of, flood forecasting or flood mapping on their own. So we've been using it, and as soon as I developed it, the 2017 hurricane season happened in the US. So we actually used it for both Texas, Florida, and Puerto Rico. And it was very interesting times because they were happening one after the other, but also a little bit frustrating for me personally because unlike international efforts where people are generally very happy to accept your help, in the US, the bureaucracy of federal agencies basically prohibit them from using your product unless they are sanctioned by, I don't know, NOAA or NASA or whoever. So I mean the Global Flood Partnership, have produced, and I was on these daily calls, listening in and watching the product that came out of NASA and others. The product that we generated at the Global Flood Partnership were often superior or better than what NASA was producing, not because NASA is not good, very smart people, it's just because they need to use specific kind of tools and images, and also they were super busy. Right? We had some people at mostly academics that had state-of-the-art tools and all that stuff. But yet, this was the only map that got any traction. And this was with FEMA. I presented it or shared it with the mailing list. It was pretty massive. And this shows potential building damage. So these points are actual address points in Texas. And I overlaid the address point of the water depth that I calculated. And when I shared this, I got an email from someone from FEMA. And he said, wow, this is really cool. How did you do it? And I told him how I did it. He said, well, can you send me the data so I can do it myself? He can't use my stuff, but he can redo it himself, right? And I guess use it. So, of course, I did. I shared it with him. I guess I used it. I don't know what happened. I'll finish with this very quickly. I'll just say this. As I said, got a little bit of traction. We got involved in a NASA project to look at coastal flooding. And coastal flooding has a whole set of other problems that we had to address. So we created a new tool, a new version of this tool to deal with coastal flooding. And pretty soon, hopefully within a few weeks, I'll submit another paper about this, but it also looks pretty good. And yeah, some recent activation or use of this tool for the Global Flood Partnership. You see the Carolinas here. Again, we kind of shared it. We did it. Why not? I don't know if it made any impact on anyone. But this one did. When you actually look, we did flooding in Sri Lanka, in Nigeria, in Laos, in where else? I don't know. There's been a busy year for flooding for the GFP. So anyway, I'll finish with that. And I don't have much time. I'm sorry for questions, I guess, but I'll take any if you want. And again, this is my email. I sit in Sherman Laboratory Building, not 5 minutes from here. So I'll be happy to meet and discuss. Thank you.
Any questions, suggestions, discussions from the audience?
I was curious with some of your modeling work that you looked at the difference between those are climate-driven kind of changes, human-induced, and looked at on dams, I think, reservoirs. Yeah. Does your climate model take into account change in sea level as for that slope calculation?
No. Well, the slope actually doesn't. That specific study only looked at suspended sediments, so the slope didn't really come into effect, and also it didn't really look. It's funny, I'm laughing because we just responded to the reviewers of that paper, and there was some comments somewhat similar to yours about looking at specific processes within the deltas, and our response was, here, this model only looks at what comes into the delta. It doesn't at all ignore what happened in the dynamics within the delta. We can only tell you with this specific model potentially how much sediment influx is coming in. Not so much what, or not explicitly how it will affect the delta itself, if that makes sense. We actually have, I have a PhD student who's actually going to look into that very explicitly. It's going to run, in addition to this model, it's going to run kind of a morphodynamic model for the delta itself, and also use remote sensing to look at changes in the extent of the delta over time, and the topography of the delta over time, and try to come up with some more informed understanding of how the impact of influxes in sediment actually affect the delta explicitly. But you're absolutely right. And sea level subsidence, all this stuff are maybe even more important in some cases than the actual changes in the sediment. It's just one parameter.
Any other?
I want to ask the temperature, obviously. So, obviously, this is a global scale temperature model, and assuming the U.S. part is doing fairly well as well. And what are taking to consider when you try to model the temperature? Was it discharge working there, land use?
I'm not gonna give you a very good answer because I didn't do the actual water modeling. But it takes air temperature, that's one parameter, and it takes the residence time of the water on the surface. And then, so if you have a reservoir, for example, actually a lot of this recent model development was done for reservoir water temperature and how it impacts ecology downstream of a dam. That was their main motivation for a lot of this, not so much for our study. So I think, and there's some other more physically based equation that I can't tell you at the top of my head. But what we found is that water temperature can vary significantly from air temperature. Once you, especially from these north-south flowing or south-north flowing rivers. When you have a river that flows along the latitude, so air temperature is more or less similar, then the temperature, air temperature, water temperature tend to be more similar because it's exposed to the same air temperature for a very long period of time. Another one is the cooling effect going down from elevation, in altitude, going down.
So elevation.
Yeah.
Yeah, because there's a lot of implication obviously for the fish, and actually even in the reservoir. So the reservoir is the places that were a lot of places they stocking the fish and also doing recreation of fish.
By the way, these groups that developed this model, they I think the specific project looked at hydroelectric, not hydroelectric, electric powers, and how, because they introduce obviously a lot of heat into the water system downstream. So if you have a river and you have a reservoir and power plant, then the impact, and they had that in their model. We didn't use that. But if you're interested, I'm sure I think they published something recently.
All right, it's 1 p.m. If anybody still has any questions or discussions, I think Sagy is still available. If not, I'd like to thank you all for coming. Please sign out on the sheet or sign in on the sheet in case you haven't done yet. We keep track of the numbers of people coming in for the EQI project, which is also sponsoring this seminar series. And with that, I would like to thank everyone and thank the speaker again.
Thank you.